Hello, welcome to another session on theory and applications of ground vehicle aerodynamics. In this session, we will look at noise, vehicle noise and noise around the vehicle, and vehicle soiling, noise and soiling. The first part, we will look at vehicle noise and the different sources of noise and how it occurs, and we'll try and differentiate between the different sources of noise. And in the second part, we will look at vehicle soiling and the effect of it on the vehicle. As a reminder, this is the main topic that we are addressing. The primary goals of the study of ground vehicle aerodynamics are the reduction of aerodynamic drag, because we get tangible benefits to the value of the vehicle, and improve fuel efficiency, which we can all use. And the second is vehicle safety. So those are our constant reminders. Why do we study this? Why do we look at this? Those are the reasons primarily. So in the study of vehicle noise or noise around the vehicle and soiling, we will look at noise first. In this portion, we will look at the sources of noise, aerodynamic noise, which is of primary importance to us, and we will look at how we locate noise source, experimental ways to locate noise source in a vehicle. And we will briefly talk about noise measurements and noise abatement tools, and then we will look at vehicle soiling as a later aspect. Okay. So, sources of noise. Noise comes from different sources, but what really is noise? We hear sound. Is every sound noise, or is it a musical instrument? I suppose it depends on whom you ask. If somebody loves rock and roll and hard rock, that might be noise to some of us, and it will be music to such persons, like my son. So let's look at the physics perspective, or the physics definition of this. That is, we want to differentiate between musical sound and noise. Musical sound results from regular periodic vibrations. So you hear something like da-dum, 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 da-dum. That's music. That's, yeah, it's periodic, it's consistent, it's predictable, and also it's not too loud. We'll talk briefly about decibels, but in that form, it's regular, it's periodic, and we call that musical sound. But when it's non-periodic, it's just like chaos, just different clattering noise, turbulence, wave collision, then it becomes noise. I suppose, like I said before, it depends on who you're talking to. Very hard, loud rock, they could say it's consistent, it's consistently loud and abusive to the ear. But generally, that's the primary differentiation between noise and musical sound. Well, let's look at the various sources of noise. The table we have here shows various types. There's the airborne noise source, there is the wind noise source, and in the wind noise source, aerodynamic noise falls into that category. There's a structure-borne noise source. But in the airborne noise, the frequency is usually between 315 hertz and 10 kilohertz, and they're the kinds of noise you get from the powertrain and from the road and chassis, road tire interaction, and the noise again from the chassis. So those would be airborne sources of noise. Wind noise is typically our aerodynamic noise. When the wind hits the mirror, hits the windshield, especially when you have a crosswind that's perpendicular to the direction of motion. That's a good radio source of noise. And head-on noise. It's easier to feel the head-on noise or the side noise, that's the lateral noise, than the tailwind noise, because the tailwind noise just smoothens into the flow and favors the flow in the direction that the vehicle is going. So that aerodynamic noise falls generally in the range between 50 hertz, which is really low, and 10 kilohertz. So is it possible that there is interaction between wind noise and airborne noise? Oh yeah, there's interaction all the time between these various forms of noises, but they can be isolated depending on the test and the experiment that's done to separate one form from the other, especially when we're trying to reduce noise. It's almost impossible to eliminate noise, but we can reduce it substantially. And that's one of the efforts that we will look at here to provide improved flow and comfort for the passenger. The other type of noise is the structure-borne noise. The structure-borne noise can range from as low as 0 hertz to 800 hertz. And that's the kind of noise we get from suspension mounts, kind of like whining noise, sometimes very tiny, but it's there, kind of like a mosquito spinning around somebody's ear. Can be annoying sometimes. The noise from engine mounts and the noise from transmission mounts. Those are the main classification of those types of noise. We've kind of essentially separated them, but they don't come that separate in nature. We just try to categorize them so we can look at the different sources that mix together to give us the noise that we have. Aerodynamic noise, that's the one of primary concern to us, the aerodynamic noise. And aerodynamic noise is essentially noise we get from unsteady flow. There's a clear difference between drag and noise. And, we can have aerodynamic drag and there's no noise. But in a way, there's some kind of relationship. It's almost certain that if you have aerodynamic noise, there will be some drag from it because the noise has some turbulence attached to it, and in that turbulent flow, we will have a drag due to the turbulent flow. So in aerodynamic noise is a result of some kind of unsteady flow, and it's caused by a separation of the flow from the reattachment of flow to the surface. We looked at when we were treating drag, we looked at the flow from the leading edge to the trailing edge of the vehicle. So when you have flow separation, for example, if you have flow separation here at the mirror and then it comes back and it hits this place, you would hear that it becomes essentially some kind of lateral noise. At least it has a lateral component that bounces from here and then hits here. And so essentially then we have separation and reattachment, except this reattachment now starts hitting like this and causes perturbation. So, and that of course is an unsteady flow. So those are kind of causes of aerodynamic noise. We have pressure fluctuation. Again, if we look at the windshield, the side shield, especially with a side wind coming to hit this, you would have fluctuation perpendicular to the direction of vehicle motion. This is direction of vehicle motion. So you will have fluctuation perpendicular to it, pressure fluctuation, which is usually more uh, uh, more obvious uh, in the glass components of the vehicle. Some vehicles have thin sheet metal, and you can actually hear the noise from the body of the vehicle. That's apart from the glass, because of the gauge that that is used in building the body material and the lack of absorption of noise in the vehicle body. It's abrupt, that's aerodynamic noise. It's abrupt, usually. It may be consistent, but typically it's abrupt, and it depends on the ambient flow condition and on the design of the vehicle. As we've just said, if it's a quality gauge that's used in building the body, the noise is not heard from the, when we talk about hearing the noise, we're talking about the passenger in the vehicle compartment, because that's the primary focus, is the noise as heard by the passenger in the vehicle compartment. And so a quality body, quality gauge body, vehicle body absorbs that noise, and so the person in the vehicle does not hear so much of it. So it depends on, again, these factors, the ambient airflow condition and the design of the vehicle. What are the sources of noise in a ground vehicle? Let's look at the car, for example. Well, this is the A-pillar. As the flow is coming, and around here you have separation of flow. It's just by design. So this is a culprit in a noise generation. It's as a source of noise. We of course have the windshield. The flow comes and it hits the windshield, and we can, depending on again how sturdy the windshield is, we could. If the windshield had been made of plexiglass, for example, we would hear a lot of flapping of it. Well, our windshields are not made of plexiglass. They are sturdy, but we can still hear the sound from the direct hit of the wind coming, because that's a direct force that's on the windshield. So the windshield is a source of noise. Gaps in doors and cracks in seals. Sometimes between this front door, end of the front door, and the beginning of the rear door, there are some gaps. How much tolerance is put into the design will affect whether noise protrudes through. The gaps in there will be sources of noise. So a high quality vehicle ensures that those things that we consider little things, they are addressed, and they are sealed. The seals, the quality of seal that's used also matters. If it's seals that crack under variable weather, especially for vehicles that are used in the northern climate, where the temperature changes from one season to the other, the seals can crack very quickly, probably even before the warranty period, and then you start to hear the noise that you weren't hearing before when you just got the car. And taking care of these and ensuring that these are addressed to reduce the noise go into the added cost in typically high quality vehicles. It's not just the engine design that makes those vehicles expensive. It's taking care of those otherwise referred to as little details. Let's look at, this is one of the ways to locate a noise source. We have a microphone in here. Right here we have a microphone that's placed on the seat right here, and it represents a person. If a person was there, they will be hearing from that position. And to experience, to find out the level of noise that the occupant would experience if it was there, we'll put that there, use other things, but typically a microphone is used. And it's positioned at the level that the occupants will be hearing. There's always going to be some level of noise experienced by occupants. The significance of it is what we're addressing, not the fact that there is noise. There's always going to be noise. And the noise that's higher than 600 hertz, and frequency of 600 hertz, and at vehicle speed above 50 miles per hour or 80 kilometers per hour becomes significant. But below that level, there's little attention that's generally paid to it. But this is one of the ways of trying to locate a noise source in the vehicle compartment. And in locating that noise source in the picture that has just been shown, we wind up all the windows. It's a lot of details. It's a laborious work. It's a hands-on approach. You wind up all the windows, tape probable wind sources, the doors, look at the gaps, seal them all. Duct tape works very well here. Removing interference components as like windshield wipers, completely strip the vehicle of that because you want to look at the vehicle, the noise in the compartment. Then we measure the interior sound level, the intensity and the frequency, and that is the reference level. That's where we use as our ground level. Then we expose what has just been measured. We expose it to wind, high-level wind, and then we measure and record the interior wind noise. And that way we're able to locate the crack, which is the source of noise. And we tape off that area one by one, tape off the first one that you locate, and go on tape off the second one. And that's how it's done step by step until the noise level is continuously being recorded, and we measure the new level. This is repeated until all the leaks are identified, and the leaks are the result of ineffective sealing. So when they're closed, then the sealing is improved, and sealing is improved. When we have, how do we know when we stop doing this? Well, ideally, when we get a recording that's equal to the value that we had before we expose the wind vehicle, the vehicle to wind. When we seal off all the levels, all the noise, all the cracks that we get, we should get a noise level that is the same as it was before we exposed the vehicle to the wind. At that point, we have done a perfect sealing. Probably almost will not do a perfect sealing, but that is essentially the guideline that's used in essence to locate noise source and correct the source. Noise measurement. Well, noise is a form of energy. It's wave energy, and it spreads out from the source and goes to the receiver. So it starts from here, a bang or something, it reaches on to the receiving ear that hears it somewhere there. So it's some form of energy, and it's generally given by intensity I, which is E over T divided by A. E is the energy, T is the time. So energy over time, that's power, and by area. So noise intensity is essentially power per unit area. And the human ear can safely detect sound intensity from 10 to the power 12 watts to about 10 to the power 12 watts per meter squared to 1 watts per meter squared. So that's, the average of human hearing is indicated as that. So the ear's response to sound is easier to describe in terms of what we're used to. That's called the decibel. So instead of using the wattage, which probably gives a psychological feeling of electric power, we use the decibel term. And the relationship between decibel and wattage is this, where the noise level is expressed in decibel beta, and beta is 10 times log to base 10, I over I naught, where I is the noise intensity that we measure, and I naught is defined as the benchmark noise level for the human ear, which is 10 to the power 12 watts per meter squared. So that is how noise is measured. Now, in-cabin noise is usually taken at a speed of about 50 miles per hour to about 70 miles per hour. In-cabin vehicle noise is usually taken at that range. In below 50 miles per hour, there's little noise that's heard. That's with all the windows up. Of course, you'll hear noise if the windows are down, and it means the vehicle occupant is not really interested in abating the noise, because if they would close the windows. Okay. Noise, again, are commonly measured in decibel CPL, the decibel SPL, and presented in the form of maximum minimum format for a given speed and road condition. We can have a qualitative noise variation with trained human ear in an entire field by itself in vibrations, and those that have experience with it are usually a good asset, and especially in high-quality vehicles where there's quietness of ride that's highly desirable by the customer, and that's human quality of having good trained human ear is an asset as a first pass before beginning measurements to find out sources of noise. Instruments that are used include microphones. We looked at one case earlier on where we have a microphone in the front passenger seat to measure the noise at the human ear level. And we use acoustic dummies also. Acoustic dummies are essentially a representation of human beings with some kind of microchip or microphone that's put there. It's also sound level meters. So these are different noise measuring instruments. So we've essentially touched the surface, kind of have a peripheral discussion on the different sources of noise and the effect of noise on vehicle and where they can come from in a vehicle as we have here that we're considering. And so the question now is, what do we do about it? How do we design from scratch? Instead of correcting, how do we design with the implementation that ameliorates noise in the vehicle? First time, do it right, first time. How do we do that? Well, there's a number of choices. One of the choices is, or not really one choice per se, we use this combination of choices, but we look at the different sources. And one of the ways that we can implement noise abatement is by using a material that reduces noise tendency, and that's something like an acoustic foam. It's an acoustic foam. Also, the acoustic barriers that are used perhaps not so much in vehicles. Acoustic barriers are probably much more used in concert halls, but it's a nice amelioration device. What's common in vehicles is the acoustic foam. That's material-based noise abatement. Design-based noise abatement, well, one of the things that we can do is look at the vehicle as a whole and look at the locations of the different aspects. Now let's start from the leading edge, the hood ornament, have it flush with the hood. It used to be, not too long ago, that the ornaments will stand up on the vehicle. And well, those are great sources of noise because the noise hits them, and they typically were not aerodynamic, which makes things even worse. And so the wind hits them, and they become sources of noise and of vibration, as a matter of fact. So improvement of hood ornament. Designers have wised up to addressing that, and most of the ornaments now, they're flush with the hood, and so the flow just goes over the ornament just as it does the rest of the vehicle, even though the ornament might be raised a little bit, but not as bad as it was when it stood exclusively clear from the rest of the vehicle in the older design. As we move to the back, we have the wipers. If the wiper shoots out of the vehicle like this, it will create a lot of noise when it's not being used. Well, of course, we expect some noise when the wiper is being used, but it's not productive to have the wiper become a source of noise when it's not in service, and that's what will happen. It will be a source of noise if it shoots out, and that we have that kind of design in some older vehicles. So one of the things to do is tuck the wiper in the hood, and so usually the hood will end somewhere here. There's some little gap here between the hood and the windshield, and the wiper is tucked in there so that when the flow is coming, the flow goes like that to the windshield and skips the wiper, because the wiper is in a little curve that's in there. So the wiper is tucked away at an altitude that is below the interface of the hood and the windshield. So essentially it's tucked in the hood at the lower end of the windshield. So that's one of the ways to improve noise from design-based. Aerodynamic antenna. Well, one of the good things that has been done is many cars don't even have the antenna showing anymore. Some don't even have the antenna, but there's still some, not many, that have antenna. Well, typical antenna design used to be just like that, and it goes to the vehicle, and it would be, the cross section would be something like that, of the antenna, just a little circle. Well, if there's going to be antenna in the vehicle, the designer might consider a cross section like that instead of that. Have a cross section like this, probably much more like this. But essentially having an airfoil tendency, rather than just having a circular tendency. This is better. This is the leading edge of the antenna. Maybe even have it more like that. This is a better design for the antenna than this in vehicle design. So we don't want a cross. We don't want a top view like this. We want a top view like this one. So that's one of the things that can be done to improve the vehicle noise reduction. That's to reduce noise in the vehicle. The A-pillar. For the A-pillar, we want a large radius, airfoil shape, contour, enclosed rain gutter. The A-pillar, in some older design, you have the A-pillar something like just like that. We don't want that, no. The A-pillar should have a smoothing effect. This is the windshield, and between the windshield and this point, the side glass, the A-pillar should be such that it follows this profile. So here's the A-pillar. It follows that profile. And it should have a large radius. The smaller the radius, the sharper the tendency for it to become, and therefore the greater the source of drag and of noise. So it should have a large radius. That will be your A-pillar. Okay, this section will be there. That will be your A-pillar, large radius, and has an airfoil shape. Again, you have something like that. You have an airfoil shape in it. So that would be the close of the A-pillar. You want something like that rather than something like that. Okay, this is preferred, and so that will be the form for the A-pillar, and enclosed one enclosed rain gutter in the design, so that there is no deflection of flow. The side view mirror, want to have aerodynamic side view mirror. Since this is the direction of the vehicle is going this way, you want a mirror that is kind of like this. Want a mirror that's like that, rather than a mirror like this. Okay, this is certainly preferred, and designers have wised up to that, and so you see most of the mirrors do that. This little difference makes a big, this little change in design makes a big difference as to whether you hear noise or you don't hear noise in the vehicle. So this is the preferred design. So have an aerodynamic side view mirror, and have the side view mirror behind the A-pillar, not before the A-pillar, but behind the A-pillar, because when the wind coming from the A-pillar will go, and if it hits the mirror, it just follows a continuous path. But if the mirror was before the A-pillar, if the mirror was here instead of here, it would cause flow separation that would just cause a lot of turbulence in this area. So you want the mirror to be behind the A-pillar. This is the A-pillar, and this is the mirror behind it. It's important in location. And of course, we want to seal the gaps. The gaps need to be sealed, and including the gaps here on the outside of the body, the interface of the body, and the glass. These are gaps. These are all other gaps too. The door handle must be flush with the body. Well, it's good to have the door handle flush with the body, but you can still reduce noise actually without having the door handle flush with the body. But it should follow an aerodynamic profile. So whether it's flushed with the body or not, it should be such that it does not cause flow to be deflected here. So again, it doesn't have to be flush with the body, but it should be such that it continues an aerodynamic profile as the flow goes along there. So that's the main thing in the design. And again, put seals in the places where there's likely to be gaps, and of course use quality seals so that there is endurance in the material that's used. Well, this is a brief overview of noise and ways to ameliorate the noise in ground vehicle. We will look next at vehicle soiling. We'll see you then.